Hey everyone, welcome back to another video about B3 maths. Today we're going to look at vectors, but in the previous video we talked about the addition, subtraction, scalar products, and products of vectors with scalars. So today we're going to talk about the vector equations of lines and the intersection of lines. So to find out or to make a vector equation of line, the process is very similar to finding the Cartesian equation of line. So for Cartesian equation of line, what do we need? So Cartesian equation of line. So we need m, which is the gradient, and we need 1 point on the line. And in the y is equal to mx plus c, this point could be, for example, when x is equal to 0, y is equal to c. And it's not just restricted to this y-intercept, it could be any point on the line. Same exact requirements are what's needed for vector equation of line. We need a point on the line. More accurately, a position vector of that set point. Let's call it A. And we need the direction vector of the line, which we can just call as B. So a point on the line is basically similar to this, and the direction vector is synonymous with the gradient, because that's the purpose exactly. Now, how does it look like? For example, so just to give you an understanding of how this is all supposed to go. So for example, we have, 2 points. Let's say you have A, and let's say we have B. And we join them with two, sorry, I think I'll have to, okay. So these are our 2 points, A and B. Now, we need a point on the line, position vector A. So this could be any one of them. It could be A, it could be B. There is absolutely no restriction that we have to start with A or B. It could be any one of them. So it could be this one also. So A could be OA, or your A could be OB also. Now, what about the direction vector? Direction vector could be AB. And we know how AB can be written. That is just simply OB minus OA. However, again, since we just need a direction, it could be BA at the same time also. It could be BA also. So that could be written as OA minus OB. So there is absolutely no restriction for that, right? Okay, so for example, let's give them numbers over here. So for example, this is 2 comma 2, and let's say this is 10 comma 5. Arbitrary numbers, nothing to do with the scaling of these grid boxes over here. So these are arbitrary numbers. Okay, so let's figure this out. So OA over here is 2i plus 2j, and OB is 10i plus 5j. And again, this could be written in a column vector also. So AB could be written as OB minus OA. So 10i minus, so plus 5j minus 2i minus 2j. So this would become 8i plus 3j. And this is our direction vector, essentially direction vector. And any one of them could be our point on the line. Now, how can we write the final thing? So just like y is equal to mx plus c. So what this gives us, it gives us a coordinate on the line. So vector equation of the line should serve the same purpose. So vector equation of the line gives us position vector instead of just a simple coordinate. This gives us a position vector of a point on the line. Okay, so this is an important point. So the point could be anywhere on the line. We have to search for that. So this could be over here, this could be over here, this could be halfway between A and B, this could be further away from B, this could be A and B themselves, but again, it could be anything. So what we need is to, since if we, for example, let's use a midpoint over here, halfway between AB. So for example, let's say M, which is the midpoint of AB. We learned about this last time. We can do OB plus OA. So half of 10i plus 5j plus 2i plus 2j. So this would be 10 plus 2, 12, 12 divided by 2, 6i plus 5 plus 2, 7, 7 over 2j, right? So this is the OM basically. But if we hadn't used this formula, what would we have done differently? What would we have done from first principles? First, we would go to OA, and then we would go to half of AB, right? So we would have done, alternatively, from first principles, first we would have gotten to OA, and then half of AB. Now this half thing is very peculiar over here because we knew that this was halfway between AB. That's why we used half of AB. If we do not know this, where this point is, what's the ratio with the AB, then we can keep it with any scalar multiple. So now the general form becomes of this particular line, R is equal to OA, A plus lambda B. So A is our position vector of the point on the line. This is our direction vector, and this is the scalar multiple with the direction vector. So this is the general form of vector equation of line. Now this process is very straightforward. There is not quite a lot in it. So we can move on to slightly more important things so we can practice together. There are two things that are important: parallel lines and intersections. So just like in the Cartesian lines, if the two gradients are the same, then that means the lines are parallel. Same way, if we have vector equations of lines, and if they are equal or they are parallel to each other even, then that means the lines are parallel. So if direction vectors are equal or parallel, the lines themselves are parallel. Right? So this is the case when the direction vectors are equal. But what happens when they're not equal? So this is the case when direction vectors are equal. When, oh sorry, direction vectors are not equal to each other. Now this could be just like in the straight lines, there could be two different possibilities. One possibility is that they intersect, and since we are also including 3D vectors into this, they could be skewed with each other also. So in 2D, there are only two possibilities. So in 2D, either lines intersect, sorry, no, either they intersect or they are parallel. But in 3D, there are three possibilities. Either lines intersect, either lines don't intersect. But when they don't intersect, this means that either they could have been parallel, that's why they couldn't intersect, or they could have been skewed. Skewed means that they are on top of each other, they are not intersecting in 3D space. Now, let's see with past paper question examples how we can differentiate between skewed lines and intersecting lines. Okay, so let's see. The lines L and M have vector equations given as these. As you can see, they have chosen different scalar coefficients, lambda and mu, just to differentiate them. Lines L and M intersect at point P. State the coordinates of P. Okay. Now, just like when we have straight lines, simple Cartesian geometry, the point where they intersect, the lines have a common point. That means that particular point lies on both of those lines. Same thing happens with here. So the position vector of point of intersection P, the R, let's say OP, on line L would be the same as coming from the line M. So this means that we have 2I plus j minus 3k. This is the reference point or point on the line for line L, plus lambda minus I plus 2k equals to 2i plus j minus 3k plus mu 2i minus j plus 5k. Now, we don't actually have to even solve this question because we can see that this is the point that's common in both of these lines. So this is the point. This is the point that's common in both of the lines. So if we cancel these out, these two are equal to each other. So this is the OP. So OP are the coordinates of P. So since this is the position vector, 2i plus j minus 3k. So coordinates of P would be 2, 1, minus 3. Easy. Now let's see another question for the intersection. Okay, so let's see this. The points A, B, and C have position vectors OA, OB, and OC. The line L1 passes through B and C. Okay. Find a vector equation for L1. All right. So what we need over here, we need either OB or OC for the A, which is the point on the line, plus the direction vector we need BC. So that's what we just simply need. So for A part, BC can be OC minus OB. So 8i plus 5j minus 3k minus 5i minus 2j. So we get 8 minus 5, that is 3i, 5 minus 2, 3j, minus 3k, right? So yeah, so position vector, so vector equation for L1 could be R equals to OB plus, since they have used mu over here, let's use lambda, BC. So OB is 5i plus 2j plus lambda. Now notice that 3 is common in all of these components. So there is a way that you can still write it as 3i plus j minus k, and you can write lambda as either 3i plus 3j minus 3k, or even you can write it as I plus j minus k, because stripped down, this is the direction vector. 3 plus 3 minus 3k is just a vector parallel to the direction vector. So if you further reduce it down, I plus j minus k can be our direction vector also. So both of these would be correct. Right. Okay. So moving on, this is the position vector equation for line L1. So either way, that's fine with us. Even you can do OC also over here, that is 8i plus 5j minus 3k. So this would also be acceptable. So I've given you two options for each of them. Line L2 has equation this. Okay. Find the coordinates of the point of intersection of L1 and L2. So we are going to do the same thing we did in the previous question. So we are just going to equate these two lines. So L1 position vector, sorry, let's call it R1 equals to R2. So this would be 5i plus 2j plus lambda I plus j minus k equals to minus 2i plus j plus 4k plus mu 3i plus j minus 2k. Now, first things first, we need to multiply the lambda and the mu inside the brackets. So 5i plus 2j plus lambda I plus lambda j minus lambda k, and this would be minus 2i plus j plus 4k plus 3 mu I plus mu j minus 2 mu k. Now we need to separate them into I, j, and k components. So I component is 5 plus lambda I. For j component, it will be 2 plus lambda j. And this is the only minus lambda k. Then we have the same thing on the right hand side. So I component, so 3 mu minus 2 I. J is 1 plus mu j, and k is 4 minus 2 mu k. Now, all we have to do further, we cannot solve it as it is, but what we can do is equate coefficients, because both sides are identical to each other. So we can equate coefficients. So 5 plus lambda equals to 3 mu minus 2. Similarly, the other one, 2 plus lambda equals to 1 plus mu. Now, first off, what we can do is we are going to solve any two equations. So we can write third one also. So minus lambda is equal to 4 minus 2 mu. So we can solve any two equations simultaneously, since we just have only two unknowns, right? So we have only two unknowns, so we just need two equations. Third one will keep for finding the k component or z component. Since we know that these lines are intersecting, so the lambda and the mu values that we'll get will be satisfying all three of these equations. So let's choose first and the second one. First, second. Technically, if you choose this one, this would be much easier. So if we choose this one, for example, third, lambda is equal to 2 mu minus 4. And we plug this into, let's say, the second one. So 2 plus, instead of lambda, we will plug into mu minus 4 equals to 1 plus mu. So this is 4. 2 minus, 2 mu minus mu, and 1 minus 2 plus 4. So this is mu equals to 4 minus 2 is 2, 2 plus 1, 3. So mu is equal to 3, lambda, which is equal to 2 mu minus 4, is 2 times by 3, 6 minus 4, 2. Now we have both of these values, mu and lambda, so we just need to plug it into the third component. So third component would be, we'll see in a second. So we just need to use either one of these values. So 5 plus lambda, so what this, did they give us a name for this? Coordinates of point of intersection. Okay. So 5 plus lambda is equal to 5 plus 2. Then the second one was 2 plus lambda, that is 2 plus 2, and minus lambda means minus 2. So this would be 7, 4, and minus 2. So point of intersection would be 7, 4, minus 2. Now let's see the next part. The point D on L2 is such that AB is equal to BD. So we have AB. Again, you see no arrow, so this means that they're talking about the length, right? Okay, this is the point that we saw in the previous video also. So point L2 says that the length of AB is equal to BD. Okay, and D we need to figure out. Okay, all right. Oh no, sorry, no. This is the same part. So first off, we need an expression for AB, and we need an expression for BD. So AB is OB minus OA, straightforward. So OB is 5I plus 2J minus OA is minus 2I plus J plus 4K. Just to make sure that I have not written them incorrectly. Minus 2, 1, and 4. Okay. So this would be 5I plus 2J plus 2I minus J, minus J and minus 4K. So this would become 7I minus J, 2 minus J, and minus 4K. So this is our AB. Now we need BD. BD is OD minus OB. So these are all vectors for the moment. Now, OD is on line L2, right? So we just have an expression for that line. We don't have the exact point. So we can use the position vector of the point on the line. So this would be, I forgot. Right, okay. So OD is minus 2I plus J plus 4K plus, I'm going to, okay, so first let's write out the same thing, 3I plus J minus 2K minus OB, and OB is 5I minus 5I minus 2J. So we will simplify this by first multiplying the mu inside, then adding the I and the J components together. So we have minus 2I plus 3. Actually, wait a second. We already did this part. We don't have to do it again. We already did this over here. We did this on this line. So let's just simply copy this, because this is exactly what we're doing. We're multiplying the mu inside, and we are separating the I, J, and K components. So we just go down and simply paste this over here. Sorry. Right. So let's make this a little bit smaller. The J is gone. Okay. So this is I, this is J, and this is K component, and minus 5I minus 2J. Okay, so let's add the minus 5 and minus 2J. So minus 2 minus 5 would be minus 7I, and J would be 1 minus 2 minus 1 plus mu J, and plus the K component remains as it is, 4 minus 2 mu K. Now We are not equating vectors, we are equating lengths. So AB length is 7 squared. Actually, it would be easier to work with the squares. 7 squared plus 1 squared plus 4 squared. So 49 plus 1, which is 50, and then 60. Oh, sorry, plus. So 50 plus 16, 66. Similarly, BD squared. So this would be 3 mu minus 7 whole squared plus mu minus 1 whole squared plus 4 minus 2 mu whole squared. Now we need to expand all of these squares before we can equate the length. Okay, so 9 mu squared, 3 times by 7, 21, times by 2, 42, plus 49, plus mu squared minus 2 mu plus 1, and plus 16, 4 times by 2, 8, 8 times by 2, 16, mu plus 4 mu squared. Now we simplify. 9 plus 1, 10, 10 plus 4, 14, mu squared, minus 42, minus 2, then minus 44, and minus 16. So that would be 60. So minus 44, so 44 plus 16. So 44 plus 10 is 54 plus 6, 60. So minus 60 mu. And then 49 plus 1, 50. And then plus 16, 66. So we know that if the lengths are equal, the squares of the lengths will also be equal. So 66 equals to 14 mu squared minus 60 mu plus 66. Now we can easily see that 66 cancels out 66, leaving us with 14 mu squared minus 66 equal to 60 mu equal to 0. Now this is all we have to solve. So one answer is simply mu 14 mu minus 60 equal to 0. So one answer leads to a trivial answer, mu is equal to 0, and the other one is 60 divided by 14. So 2 times by 30 and 2 times by 7, so 30 over 7. Now this mu can be plugged right over here because that was the representation of OD. So OD three mu minus two I plus one plus mu j plus 4 minus 2 mu k. So mu is 30 over 7. So 3 times by 30, 90 over 7 minus, since we're going to be adding with 2, so let's do 2 times by 7 over 7 I plus mu itself is 30 over 7, so we can add 7 over 7 over here, j plus same thing, 4 times by 7 over 7 minus 2 times by 30 is 60 over 7. Okay, so 90 minus 14 is 76 over 7 I plus 37 over 7 j plus 28 minus 60, so 60 minus 30 is 30, so plus 2, 32 over 7. Okay, and that's the position vector of D. That's what we had to find, right? Yeah, position vector of D. Okay, now let's see another question, but for skew this time. All right, so let's see this. The points A and B have position vectors are given. The line L has equation this. Show that the line does not intersect the line passing through A and B. Okay, so the difference between this and the one question that we did before is that when we have three equations, because we are talking about three dimensions over here, so we are equating position vector components of these 2 points. So the lambda and mu values that we get for this one will not satisfy the third one. So this is the difference between the lines intersecting and the lines not intersecting. So the lines, if we get lambda and mu, the third, if the third component, both sides are equal, that means the lines intersect. If both sides do not do not match, that means the lines do not intersect. So let's see this into practice. So first off, we need the line equation of AB. So line AB first. So we can do R equals to OA plus lambda. Since they've used mu over here, so we can use lambda AB. So this would be 2I minus j plus 3k plus lambda. Remember, AB can be written as OB minus OA. So OB is I plus j plus 5k minus 2I plus j minus 3k. So as you notice, the signs are changed because of the negative sign. So minus I plus 2j plus 2k. So minus I plus 2j plus 2k. So 2I minus lambda I minus j plus 2 lambda j plus 3k plus 2 lambda k. Now we separate them into ijk components. So 2 minus lambda I minus plus 2 minus 2 lambda minus 1j and plus 3 plus 2 lambda k. So this is the parametric form for this vector equation of line. Now the other one, line L, we are going to repeat the same thing. So I plus j plus 2k plus 3 mu I plus mu j minus mu k. So this would become I plus 3 mu. So 1 plus 3 mu I plus 1 plus mu j and then 2 minus mu k. So now we can equate both of these together. So equating two equations. So you have 2 minus I plus 2 lambda minus 1 j plus 3 plus 2 lambda k identical to 1 plus 3 mu I plus 1 plus mu j plus 2 minus mu k. Now we equate coefficients same way as before. Equate coefficients. So 2 minus lambda equals to 1 plus 3 mu. 2 lambda minus 1 equals to 1 plus mu, and the last one, 3 plus 2 lambda equals to 2 minus mu. Now, since we have two unknowns, we're going to solve two equations one by first. So two equations first, then plug lambda mu in the third one. So we can choose either one. There's absolutely no problem over here. So this is first one, this is second one, this is third one. So let's choose, let's say you have second one. So you can make mu equals to 2 lambda minus 1 minus 1. So this would be 2 lambda minus 2. So now we plug this into 1. Actually, we can plug this into third one, easy one. So 3 plus 2 lambda equals to 2 minus mu, that would be minus 2 lambda, and plus 2. So 3 plus 2 lambda equals to 4 minus 2 lambda. So 2 lambda plus 2 lambda is equal to 4 lambda, and 4 minus 3 is basically 1. So lambda is equal to 1 over 4. So therefore mu will be 2 times by 1 over 4 minus 2. So 1 over 2 minus 2. So 1 over 2 minus 2 would be minus 3 over 2. Now plugging in these into the third one, which is going to be the first one now. So plugging lambda mu in first one, because we solved second and third, so there's no need to plug them back again. Same thing. So we need 2 minus lambda, and we have 1 plus 3 mu. So 2 minus lambda is 2 minus 1 over 4, and 1 plus 3 times by minus 3 over 2. So let's simplify this. So times by 4 times by 4. So 8 minus 1 is 7 over 4. So this is 1 minus 9 over 2. So times by 2 times by 2. So 9 minus 2 is 7 over 2. So as you can see, these are not equal. Okay, because of this 4 and the 2, they are not equal. Therefore, lines do not intersect. If they were intersecting, the third component would match on both sides. All right, let's move on to the next important thing, which is the angle between lines, or angles between lines. So whenever we're concerned with angles between lines, we just have to work with direction vectors, because angles are decided by directions, so we just have to look at direction vector. B1, B2, whatever they are. So since we're talking about vectors, we have to recall the scalar product. So B1 dot B2, magnitude of B1, magnitude of B2, cos of theta. So this would be the angle between the two lines. So B1 dot B2 divided by magnitude of B1, magnitude of B2. Now, if recalling the scalar product discussion, if theta is equal to 0, lines would be parallel, or vectors would be parallel to each other. Similarly, if theta is equal to 90 degrees, B1 parallel, so B1 dot B2 would come out to be 0. And similarly, if they are parallel, B1 dot B2 would be equal to the product of the magnitudes. Any other intermediate angle between them can be found out by this formula. So let's see an example. Okay, so let's see. The lines L and M have equations, this given. Relative to the origin O, the position vector of the point P is this. All right. Given that L is perpendicular to M, so when L is perpendicular to M, that means these direction vectors would be, their scalar product would be 0. And that P lies on L, find the values of constants A, B, and C. Okay. So first off, we need to apply L perpendicular to M. So L perpendicular to M means the scalar product of CI minus 2j plus 4k dot 2I minus 3j plus k equal to 0. So c times by 2, 2c, and then minus 2 times by minus 3, that is 6, and then 4 times by 1, 4. So 10, so c would be minus 10 over 2, that would be minus 5. So one constant done. All right, now only two A, B, and are left. Now the position vector of the point P is given as OP 4I plus 7j minus 2k. And this lies on the line R equals to AI plus this was the direction vector, right? So lambda ci plus 3j minus 2 lambda. Actually, let me zoom out. Yeah, okay, sorry. So minus 2 lambda j plus bk plus 4 lambda k. All right. So this would mean that this is a plus lambda I. Then we have 3 minus 2 lambda j, and then we have b plus 4 lambda k. So the coefficients will be matching these 2k. So first off, as you can see, this and this component has unknowns. So first we can find out the appropriate lambda by using this one. So 7 equals to 3 minus 2 lambda. So that means in three unknowns, a, b, and lambda, we can find out first one of them. So 2 lambda is equal to 3 minus 7, which is minus 4. So lambda is equal to minus 2. Now we apply this lambda into the rest of the equations. So my bad, this is lambda c. So lambda c. So a plus lambda c. C we have already found out, lambda we have already found out, that is equal to 4. So a is equal to 4 minus lambda is minus 2 and C is minus 5. So 4 minus 10, that is minus 6. Right. So A is also now known. Now we move on to B. So B plus 4 lambda equals to minus 2. So B would be minus 2 minus 4 lambda is minus 2. So minus 2 plus 8, which is 6. So therefore, A is equal to minus 6, B is equal to 6, C is equal to minus 5. Now, before we answer the last part of this question, we need to revisit a very important concept, which is the shortest distance between a point and a line. So what that means is, for example, this is your line and this is your point. Let's call it point P and line L. So the shortest distance between them is actually a perpendicular line segment that joins both the point and the line. And the point of intersection between them is called the foot of the perpendicular. So this is something that we must remember. Now, the points to note over here that we have figured out what the shortest distance is and how to figure it out, but we need to do the math also a little bit. So we know, let's call this Q, right? So OQ, which is the position vector of the point on the line, that is given by the vector equation of the line. So A plus lambda B, which is the vector equation of line L, right? Similarly, there is another point over here, is that QP and the direction vector for B would have a scalar vector 0, because this QP, we have already said that this is a perpendicular line segment. So this QP is perpendicular to the line L, and we know that we just need the direction vector for this purposes. When we were finding the angle between the lines, we also just simply use the direction vector. So this is the point that connects them. So first we find out an expression for OQ, use that for QP, OP minus OQ, and then have a scalar product with the direction vector of the line, and that would be equal to 0. And that would be sufficient information for us to figure out the foot of the perpendicular or anything else also. Okay, so let's see an example for this thing. All right, so let's see this. The points A and B have position vectors given, and the line L has equation this. Show that L does not intersect the line passing through A and B. So this is another question that is asking us about the point of intersection, or whether or not it intersects or not. So we're going to repeat the same process. So we need L does not intersect the line passing through A and B. First, we need to have an expression for line passing through A and B. So first off, we need AB, which can be written as OB minus OA. So OB is 2I minus J plus K minus I plus 2J minus 2K, which becomes 2I minus I minus J minus 2J minus 3J, and plus K plus 2K, which is going to be plus 3K. So this means that the vector equation of line through AB can be written as OA I plus 2J minus 2K. Since they have used mu over here, we can use lambda. Direction vector is I minus 3J plus 3K. Now this is the equation of the line. To convert it into the parametric form, we lump the I, J, K components together. So I plus lambda I, so 1 plus lambda I plus 2 minus 3 lambda J and 3 lambda minus 2 K. Now this is the parametric form. Now we need to equate these two equations. So equating, let's call this L2, L2 and L. So we have 1 plus lambda I plus 2 minus 3 lambda J plus 3 lambda minus 2 K identical to I. We are going to do the same thing with this line. So I plus 2 mu, sorry, 1 plus 2 mu I. Then we have minus J minus 3 mu. Okay. So we can do this, or plus minus J minus 3 mu. Oh, sorry, minus 1 minus 3 mu J plus, then we have 3 and plus 4 mu. 4 mu K. Right. Now we equate the coefficients now. So 1 plus lambda equals to 1 plus 2 mu. Then we have 2 minus 3 lambda equals to minus 1 minus 3 mu. And the third one, 3 lambda minus 2 equals to 3 plus 4 mu. So as before, we are going to equate simultaneously any two of 3 of them. And then we will plug the lambda mu in the third one. So for example, this is the first one, this is the second one, second, and this is the third one. So let's choose the first and the second. First and second. So in this case, if you notice, we can isolate lambda by cancelling out the 1 and 1. So lambda is equal to 2 mu. Plugging it, this is the first one. Then plugging it into the second one. So 2 minus 3, 2 mu equals to minus 1 minus 3 mu. So this becomes 2 minus 6 mu equals to minus 1 minus 3 mu. So mu's go on the other side. So 6 mu minus 3 mu, and 2 plus 1, 3. So this is 3 mu equals to 3. So mu is equal to 1. That makes lambda is equal to 2. Now we plug these two values plugging lambda and mu in third equation to see whether this matches or not. So 3 lambda minus 2 and the 3 plus 4, 1. So 6 minus 2, 7. So 4, 7. So basically, as you can see, the left hand side does not match the right hand side. So therefore, lines do not intersect. Right. Okay. Next up, we have find the position vector of the foot of the perpendicular from A to L. Right. Okay. So first, let's write the key components necessary. So OA was I plus 2j minus 2k, and the line L is R is equal to, let's continue writing this in the parametric form. Basically this form, so 1 plus 2 mu I plus minus 1 minus 3 mu j and 3 plus 4 mu k. Just to make sure that we are writing the correct, right. Okay. Now, we know if this is L and this is our point A, this is going to be perpendicular. So this point, let's call it Q, foot of the perpendicular Q. So AQ is going to be perpendicular to the direction vector. Actually, sorry, we did not need that. My bad. My bad. Sorry, we did not need that. So I minus j plus 3k plus mu 2I minus 3j plus 4k. Right, okay. So first off, we have 2 points to see over here. Is that OQ first, OQ has the same position vector. Over here, we actually had to write that. So 1 plus 2 mu I plus minus 1 minus 3 mu j plus 3 plus 4 mu k. This is the position vector for OQ. However, now we know that since it is the foot of perpendicular, is that the second point will be that AQ is perpendicular to the direction vector 2I minus 3j plus 4k equals to 0. So these are the 2 steps that we have to go through. So finding the AQ is easy because we have already written this in the parametric form. So this will going to be OQ minus OA. So OQ minus OA, so 1 plus 2 mu minus 1, that just becomes 2 mu I. Then we have minus 1 minus 3 mu minus 2, that will become minus 3. So minus 3 minus 3 mu j and plus 3 minus 2. So that would be 5 plus 4 mu. Okay. So this is our AQ. Now we apply the second point. So AQ dot the direction vector of line L is 0. So 2 mu times by 2 plus 3 minus 3 minus 3 mu times by -3 plus 5 plus 4 mu times by 4 equals to 0. Now let's uh, expand and simplify. So this becomes 4 mu. Uh, all the signs will become positive because it's -3 and -3 inside. So this is 9 plus 9 mu, and this will become 20 plus 16 mu equal to 0. So 4 plus 9 is 13. 13 plus 16 is 29 mu, and this is 9 plus 20. Sorry, this is 9 plus 20, 29 equal to 0. So this becomes mu plus 1 equal to 0. So that becomes mu is equal to -1. Just simply divide both sides by 29. Right, okay. Since we have mu is equal to -1, we needed the position vector. Okay, all right. So we just need to plug it into the line L. We just need to plug it over here. So 1 plus 2 mu, therefore OQ, 1 plus 2 mu, that would become -2. 1 plus 2 mu, yeah, okay. So 1 minus 2 I, then it was -1 -3 mu, yeah. So -1 -3 mu, so -3 times the -1, that becomes +3j, and 4 minus 2 mu, sorry, 3 plus 4 mu. So 3 plus 4 mu, that becomes -4. Okay. So 1 minus 2 is -I plus 2j minus k. And that's the answer. That's basically all we had to do. All right. Since we're talking about the same concept, there's another concept also which is very similar and is an extension of this. Questions often come for that about a reflection of a point in a line. So we know this from the IGC also, that if we need, let's say for example, this is point A, this is line L, and we need to find the reflection of point A in the line L, it's not only same distance from the line L, it's the line connecting the original point and the image is also perpendicular. So not only these two things, let's call it Q, AQ and A dash Q are equal, but this is also perpendicular to the line L, right? Okay, so let's see in a question to see this type of problem also. Okay, let's see this. So relative to the origin O, the position vector, point A has position vector given by OA. The line L has equation this. Find the position vector of the foot of the perpendicular from A to L. Now the first part of this first part is same thing as what we did for the previous question. So we know that, let's call OQ the position vector of foot of the perpendicular. from O to L, from A to L, sorry, my bad. So that would mean that not only OQ will be expressed by the same expression, 3i minus j plus 2k, which can also be written as in the parametric form 9 plus 3 mu I, and this is plus minus 1 minus mu j plus 8 plus 2k. So 8 plus 2 mu k. Right, so these are two descriptions for okay. Second point is that the AQ is going to be perpendicular to line L, or only the direction vector of this, since they are perpendicular. So we first need to find out AQ, which is going to be OQ minus OA. Now we can use this parametric form over here. So OQ minus OA, so 9 plus 3 mu minus 1, so that is 8 plus 3 mu I plus minus 1 minus mu minus 2, that becomes minus 3, 8 minus 4, 4. Okay, now AQ, so basically we just need to do this. So 8 plus 3 mu times by 3, 8 plus 3 mu, then minus 1 times by minus 3 minus u plus 2 times by 4 plus 2 mu equals to 0. Right. So what we have, okay, so 24 plus 9 mu plus 3 plus mu plus 8 plus 4 mu equal to 0. So 9 plus mu, 10, 10 plus 4, 14 mu, and 24 plus 8, that is 32, 32 plus 3, that is 35. So as you can see, these coefficients are divisible by 7. So when you divide this equation by 7, this leads to 2 mu plus 5 equal to 0. So mu is minus 5 over 2. Now this we have to plug in this. Oh, sorry, no. In this OQ. So therefore, OQ would be 9 plus 3 times by minus 5 over 2. So minus 15 over 2. So I'm just going to multiply 2 by 2. Then we have minus 1 minus mu. So this would become plus 5 over 2 times by 2 times by 2 j plus 8 plus 2 mu. So this would become minus 10 over 2 and times by 2 times by 2 k. So we have 18 minus 15, 3 over 2i plus 5 minus 2, 3 over 2 j, and 16 minus 10, 6 over 2, that is going to be 3k. So this is our foot of the perpendicular. Now, the second part was hence find the position vector of the reflection of A in L. All right. Now, first let's draw a diagram of what we have. So this is line L. This is point A, and its reflection would be, oh, sorry, right. Oh, so this would be its reflection. So if this is point A, this is point image, and this is our foot perpendicular. We designate it as Q, and this is this. Right. Now, to find out the position vector of A, what we can do, OA dash, we can go to OA first. Let's say, for example, if this is origin. So first we can go to OA, and then from A to A dash. And we know since it is twice the distance of AQ, so we can write it as 2AQ. And we also have AQ. This was the description of our AQ, which we can also use now. So OA, that is I plus 2J plus 4K plus 2 times by, actually let's, right, sorry, my bad, because we needed space to write the parametric form of AQ. So AQ is 8 plus 3 mu, so 8 minus 15 over 2, so 8 minus 15 over 2, I plus minus 3 plus 5 over 2, plus, and 4 plus, sorry, 4 minus 10 over 2. So this part was J. Right, okay. So we have over here I plus 2J plus 4K plus 2 times by 8 minus 15 over 2. 15 over 2 is 7.5. So you'd be left with half of I. Then 5 over 2 is 2.5. So minus 3 plus 2.5 is also minus half. J. Sorry, this is we don't need over here. And then 10 over 2 is already 5. So that would be minus K. Now we multiply the 2 inside. So I plus 2J plus 4K plus I minus J minus 2K. Now we simplify. I plus I is 2I, 2J minus J, J, and 4K minus 2K is 2K. Sorry, this is plus. All right. So now let's look at 3D problems which we encounter in exams. All right, so let's see this question. So in the diagram, OABCD is a solid figure in which OA is equal to OB equals to 4 units and OD is equal to 3 units. Okay, we are talking about the length. The edge OD is vertical, so we're talking about this edge. This is vertical. DC is parallel to OB, so DC is parallel to OB, that means it's in the J direction. The base OAB is horizontal and the angle AOB is 90 degrees. We already know that the angle between I and J unit vectors is 90. Unit vectors I, J, and K are parallel to OA, OB, and OD respectively. Okay. The midpoint of AB is M and the point N on BC is such that Cn is equal to 2NB. Okay, so one by one we need to decode this information that is given to us. So first off, OA and OB, they are in I and J directions respectively. So OA would be 4I and OB would be 4J, just to make sure. Yeah, so B is in J direction. And OD is 3K. So OD is 3K. Right. Okay. Now we know that C, if we want the position vector of C, we can go through OD and then DC. Because DC, they already gave us that it is 1 unit and it's parallel to OB. That means 1J. So DC is simply just J. So this means that we can go to OC by first going to OD, and plus DC. So OD is 3K and then DC is J. So basically J plus 3K. All right, we have got OC now. Right. Similarly, we have Cn is equal to 2NB. So this means that when we have CB, CB can be broken into Cn and NB. So they have given us that Cn is equal to 2 times by NB, or NB is half of Cn. Either way you can decode this information. So let's rewrite it two different ways. So this is Cn plus NB. So if we replace Cn by 2NB, we get this. So this means that CB is 3 times by NB. And we are talking about vectors. So the notation, the arrow notation has to be clear. What if we have an alternate description for CB in terms of Cn? So NB is half of Cn, and this is Cn also. So we will get 3 over 2 Cn. Now we can use either one of these descriptions when we need them. All right. So the question A part was express the vectors MD and ON in terms of I, J, and K. All right. We know that M is the midpoint of AB. So first off, OM is half of OA plus OB. So half of OA is 4I and 4J. So this would become 2I plus 2J. Right? Similarly, we can do MD, position vector notation, OD minus OM. So OD is 3K and minus OM, minus 2i minus 2j. So you can write it as minus 2i minus 2j and plus 3k. Now we need on. On. So there are two ways to go about this. Let's change the color a little bit. So what we can do is we can go to OC and then CN, which is going to be parallel to CB. So, sorry, this way. Or alternatively, you can go to OB and then BN, which is the opposite of NB. So both ways are available to us, so we can check from both the ways to see whether we get the right thing or not. So let's put partition in the middle. So ON, first let's go to OC and then CN. The other way would be OB and BN. Either way, we're going to get the same answer, but just for the sake of practice, we're going to see alternate descriptions. OC, we found the vector for that, j plus 3k, and Cn would be 2/3 of CB. We actually need CB first. Okay, we'll figure this out. So 2/3 of CB. Actually, first let's write this. So CB, in terms of position vectors, can be written as OB minus OC. So OB is 4j and OC we figured out to be minus j minus 3k. So this is 3j minus 3k. So this is CB. So 3j minus 3k. So we will get j plus 3k plus 3 cancelled. So you will get 2j minus 2k. So j plus 2j, 3j, and 3 minus 2k is plus k. Similarly, let's try the other way around. Remember that bn is minus nb. So OB, we had 4j, and bn, did we have bn? Oh, sorry, or nb, right? We had over here. So first we can figure out what NB is. NB is 1/3 of CB, and NBN would be minus 1/3. So minus 1/3 of CB, which we figured out to be 3j minus 3k. So 3 again cancel. So you will have 4j minus j and plus k. So again you have 3j plus k. So this is our ON. Now calculate the angle in degrees between the directions MD and ON. Right. So for that we need the scalar product, and we will also need the lengths. So length of MD and the length of ON. So MD length would be 2 squared plus 2 squared plus 3 squared And this would be 4 plus 4, 8, 8 plus 9, 17 square root. This one is 3 squared plus 1 squared. So this would be square root of 10. Next, we need the dot product or the scalar product. So MDON equals to length of MD, length of ON, cos of theta. So MD is minus 2I minus 2J plus 3K, and ON was 3J plus K equals to root 17, root 10. When we multiply, we get root 170 cos of theta. Now, if you notice this I and j thing, there is no I component in the second vector, so 2 times by 0 is 0, minus 2 times by 3 is minus 6, and 3 times by 1 is 3. So this would be equal to this thing. And finally, cos of theta would be minus 6 plus 3 is minus 3 root 170. So theta would be cos inverse of minus 3 over root 170. So let's solve for that. This is in pi. When we convert it into degrees, this is 103.3 degrees. So 103.3 degrees. Right. Okay. Show that the length of the perpendicular from M to ON. Okay. So from M to ON. So let's erase these. From M to ON. And remember, it's the perpendicular always. Okay, so we always we saw that in previous examples also, that the shortest length between a point and a line is the perpendicular that joins the point and the line, and the 90 degrees is at the end, is on the line. It cannot be on the point. So we are going to do the same thing we did before. First off, we need to figure out what the foot of the perpendicular is. Then we figured out, then we have to figure out the length. First off, the same thing as before. OQ, since this lies on ON, OQ, since this already lies on ON, and O is one of the points that lies on the line ON, so we can write it as lambda ON. Then the second point that we are going to use over here is that the OQ or even ON, when we have a scalar product with NQ, would be 0. This would lead us to finding the OQ. Actually, this would lead us to find lambda, which we would just plug into OQ to find out ON. Oh, sorry, no, we already just okay. So then for the length, we would plug it into MQ. First, we will find out the vector, then the length. All right. Now, let's carry on with this. So, C part. Now, we wrote above that ON is lambda, OQ is lambda ON, which is lambda times by that was 3J plus K 3j plus k, which can be written as 3 lambda j plus lambda k. Then we also need mq, which can be written as OQ minus OM. So OQ is 3 lambda j plus lambda k minus OM, which was minus 2 plus, sorry, minus 2i minus 2j. Oh no, sorry, just 2i plus 2j. Okay. Minus 2y minus 2j because the sign was negative. So we have to lump the j components together. So this is minus 2i plus 3 lambda minus 2j and plus lambda k. Anything else that we need? Right, okay, now we can go on to the dot product, that the on dot mq is 0. So when we expand this, on is 3j plus k dot mq is this entire thing, 2i plus 3 lambda minus 2j plus lambda k is equal to 0. Since there is no I component, the I component would be 0, but this would be 3 times by 3 lambda minus 2, and the other one would be 1 times by lambda, lambda equal to 0. So we will have 9 lambda minus 6 plus lambda equal to 0. This would become 10 lambda equal to 6, and lambda would be 6 over 10, which is going to be 3 over 5 or 0.6. However you want to write that. Now what we need is we need to plug this into the MQ description. So we plug this into MQ. So MQ, sorry, first we need to find the vector. So minus 2i plus 3 lambda, that is 3 times by 0.6, that is just simply 1.8. 1.8 minus 2, that is minus 0.2. So 1.8 minus 2, that is minus 0.2. Other way around, you can use the fractions also. So 3 times by 3, that is 9 over 5 minus 2, that you can do this. So you will get 9 minus 10, that is minus 1 over 2, exactly what this is. So you can use minus 1 over 2 j plus 3 by 5 k. Now we need the length mq, and this would be 2 squared plus 1 over 2 whole squared, and then 3 by 5 squared whole under root. So 4 plus 1 over, sorry, wait. This was 1 over 2. Oh no, sorry, 1 over 5, my bad. 1 over 5. 1 over 5. This is 1 over 5. So this is 1 over 5, my bad. So this is also 1 over 5. So this would be 1 over 25. And this is 9 over 25. And you can write it as 25 times by 4 over 25, and then whole square root. So this would become 100 plus 1 plus 9, that is 110 over 25. When we divide both the numerator and denominator by 5, we will get 5 times by 5 and 5 times by 22, 22 over 5 square root. And I guess that was what we needed to show. Yes, as you can see, that was what we needed to show. And that's about it for the vectors. So you can practice with more past paper questions and you will see that the general theme I have all covered. So hopefully we will see each other in the next video with the next topic. And if you like my teaching and would like some personal one-on-one, you can join using the links shown. You can join the Calendly. You can book an appointment for one-on-one. Or if you want to join the group sessions, you can also see the schedule of open classes. Usually, not a lot of students show up in those open classes. So if you either want to join one-on-one or if you want to join group one, you can still join that. All right, so see you in the next video.